metal packaging, just so that the class is aware, I worked for NAPAC, National Amalgamated Packaging in South Africa for 13 years in the metal cluster. And in that role, I've been involved with quite a number of metal packaging projects, you know, firstly, you must know metal is made up of two substrates. Metal is a substrate in packaging, which goes with paper, glass, board, plastic, and metal. Okay, so those are the basic packaging substrates. I'm going to be talking about metal, and I'm saying that metal in itself can be split into two categories, and that is tin plate or ferrous, or sometimes known as steel packaging, and the other is aluminium. So those are the two broad categories within the metal substrate. And as I was saying, I've worked for NAPAC for many years in both the substrates, especially, you know, with projects relating to material thickness reduction, gauge reduction and things, without compromising the integrity of the packaging format itself. So, so that's a bit of background of my direct exposure in the industry. Of course, over the past 32 years, I've been lecturing packaging substrates for the Institute of Packaging South Africa and for the World Packaging Organization. So, metal packaging. Now, let's just kick straight into it. So as I said earlier, there are two basic substrates: electrolytic tin plate, sometimes known as ETP, and then there's aluminium. So we divide these, that's design, we divide this packaging options into those that are designed for a hermetic seal. What is the meaning of hermetic sealing? H-E-R-M-E-T-I-C. It really means airtight. Means that there is no air ingress into the packaging. Now, generally, when you think of packaging like paper and board and I wouldn't say plastics, paper, board, mostly paper and board, you do not worry about air ingress. But when it comes to metal packaging, particularly aerosols and food packaging, you cannot have air going into or leaving the can. So the word is hermetic sealing. Then, broadly speaking, metal packaging is used for, in the first category, the food containment. Then you've got aerated beverages. So this is aerosols. No, sorry. Aerated beverages would be soft drinks, carbonated soft drinks, CSDs. These are acronyms that we use in industry, and if you're not familiar with them, perhaps it would be a good idea to just scribble it down, and so you can use these acronyms in your emails and discussions and meetings and things, because this is how, I mean, how do you actually say to somebody, look, last week I've been in a whole week of training in Nigeria. The way to demonstrate that is to use the language of packaging. So aerated beverages are what? Carbonated soft drinks. So that would be all the beer cans, all the Coke and the Fanta and all these soft drinks and beverages. Then there are aerosols. Aerosols are a niche metal packaging in the sense that they are pressure vessels. So in terms of the OSHAC, the Occupational Health and Safety Act, they fall under what is known as pressure vessels because they are expected to withhold a pressure of at least 12 bars. It's quite a significant pressure, 12 bars. And then there's basic metal containers, which is all of the I mean, there's a lot of decorative tinware and all of that, which falls into basic metal containers. So that's metal packaging. If you were not aware of what they were all about, then now you have some idea. Should have had some pictures here of packaging that shows you the various categories of those. So the basic raw materials, let's talk now only tin plate. The basic raw materials are cold rolled steel. So cold rolled steel, or CRS, and electrolytically tin plated steel, or EPS, or galvanized steel, or stainless steel. These are all packaging formats. And then there are seaming compounds that are used to join sections of the metal packaging together in a double seam. So in the double, which I'll speak about at length just now, but just know this, that in the metal packaging, there is a part of the packaging which you have never ever given thought to, unless you are in the metal packaging arena. But as a consumer, you have seen it a zillion times, but you've never wondered what is inside it. It's the double seam. And today, we'll unpack the double seam and show you what is inside. So the seaming compound is made up of rubber and elastic materials that are roller coated or sometimes sprayed on, mostly sprayed on in a circular fashion on the ends of a packaging. Yeah, that word end might not mean much to some of you, so I will show you what I mean by an end just now. And then why do we put in a sealing compound or a seaming compound? Because it has to be chemically resistant to the packaging content. So typically in the packaging content would be, in this case, food or fish or something like that. So the seaming compound has got to be completely resistant to the content, and it will fill the voids. But the voids, what we mean by the voids, inside the double seam, which I'll explain to you just now. So what is the actual manufacturing process flow? So what we do, firstly, the material, tin plate, is supplied in a reel. Now, just as you get a reel of board or you get a reel of paper, it's called a jumbo reel. Does anybody know, typically in paper, what is the width of a reel that comes off a mill? I know Pierre has already spoken about paper and board. So just a question. Typically, what is the length of the reel? No, sorry, not the length of the reel. The length of the reel could be 5 or 6 kilometers. I'm talking about the width of the reel. Any guesses?
Anybody want to guess? Nobody has an idea.
2.4.
Yeah.
2.4.
Yeah. And that's think about it exactly. You think about it, put your hands out and see what a meter is, then what another meter is, and another half meter, 2.5 meters. It's called a decal. Now, typically in metal packaging, you may not get up to that width, but I just wanted you to have that idea. With metal packaging, the coils, we call them a coil, slightly less, could be 1.5 meters, a meter, 1.2 meters, and so on. What we then do is, as with the paper, we decal the paper and we then present it to a slitting process, where the slitter in the slitting process will reduce the paper to specific dimensions, which is then stacked onto a pallet. So this in metal packaging is known as stillage, a stillage, so that now we can print on the cut metal sheets one at a time. So what happens before we print, though? We've got to take the sheets and we've got to lacquer it. Or sometimes we use the word sizing. So we size it by typically a roller coating process. We roller coat it and then we cure it for 20 minutes at 165 degrees. Then we coat it with a white coating. Remember, the tin plate is silver. The tin plate is silver. Now, just remember that this electrolytic tin plate is silver. That silver color has come from the tin plating process. So what is the tin plating process? It is an electrolytic process that applies ionic tin, which in the periodic table that Pierre was speaking about earlier, tin is known as stannic or stannous. So SnCl2 is stannic chloride. What is stannic chloride? It is an ionic compound. When in water, it then separates into Sn2+, which is a positively charged ion, and Cl-. There are two Cl minuses, which then balance out the Sn2+ plus the two Cl minuses. Therefore, the ionic compound is known as stannic chloride or SnCl2. Now, in solution, these break up into Sn2+ and Cl-. Now, what happens is, if you negatively charge the steel, which, by the way, when it's mined and rolled out, cold rolled steel, it is black in color. So we can't use it in packaging when it is black in color. Therefore, we electrolytically tin plate it, ETP. How we do that? We dip the steel, which is black, into a pool, literally like a swimming pool of stannic chloride solution, and we draw it out on the other end. But by the way, this is done before the sheeting. Huh? So it's unwound from one coil and it is rewound after it gets through the pool. But what happens in the pool? We apply an electric current and we deposit the Sn+ onto the surface of the negatively charged steel. And we get a deposition of tin, which is Sn, onto the plate, onto the steel. Therefore, the tin plate is now looking silver. Now, okay, now that I've discussed that, now we're going to start here. We lacquer and we coat, then we cure for 20 minutes. By the time we do this and it comes out of the oven, remember these things are done in one sheet at a time. So it actually goes in through the oven, one sheet at a time as well. What happens is when it gets into the oven, the sheets are picked up by a carrier, a steel fabricated carrier, and all the sheets are then lying up. They stacked, they kind of resting on the carrier, and it's moved through the oven for 20 minutes, generally 20 to 25 minutes, 165 degrees Celsius, and that cure or lacquer or size and the coating is cured. It's those things are done independently. The first the size, then the lacquer, and both are cured. Once the sheets are cured and they are dry, they are now, once you got the coating on, and typically the coating would be white, although there are some customers that may want a yellow or a blue coating or whatever. So we give the customer what he wants, but typically it's white, because it's on white that we can print the next stage, which is printing. Now we then print this 4 colors, 5 colors, 6 colors, 7 or 8 colors. Maybe we print 4 colors at a time. We then cure it 20 minutes again, 165 degrees. And why I've got the QC at the back here is because after each of these bakes, the QC will check the degree of cure and the film weight that was applied. So these are some of the tests that are done to make sure that the sheets are cut, are printed correctly. It's then slit into blanks. So in other words, on the one sheet, let's say the sheet is 1 meter by 800 millimeters, which is not really a square, it's a rectangle. So, and I want to print, let's just say a can out of it. I can probably get 4 cans across and 6 cans down. So 6 fours, maybe I'm going to get 24 cans out of this sheet. Are we with me? Yeah? So when we print metal packaging, we do not print 1 can up. We print 8 cans, 10 cans, 20 cans, 24 cans, could be 30 cans up, depending on the sheet size and the can dimension. Now, we then slit the sheet into blanks. Each blank then represents 1 can. These cans are side welded and rolled and side welded, and the welds are protected. So when it's side welded, After the side welding, you've got to get a spray over it. Why do we put a spray over it? It's simply because that part of the weld where you side welded is not covered by paint or varnish. If you covered it by paint and varnish, you will not be able to weld over it. So you've got to have it naked. Once you weld over it, you have to protect it because there's no paint and varnish. Remember, the paint and the varnish will protect the rest of the tin plate because they won't be able, the water, atmospheric humidity will not be able to attack the steel because you've got a coating on it. But at the weld, it can. So we protect it both on the inside of the can and on the outside of the can. Once that happens, you now have a cylinder, a hollow cylinder. That cylinder is then flanged. I'll show you pictures of this just now so you can see it. Once it's flanged, we then add the components or the ends on the top and the bottom, and we have double seam these ends onto the body of the can. Hence, we talk about a three-piece can. What do we mean by a three-piece can? The center body, which is flanged, and the top component and the bottom component. And that makes up a three-piece can. Then, of course, with the several dimensional checks that are done on the can, it's packed and it is distributed. That's simply the process.
At this factory, they make 1,100 cans every minute around the clock. That's more than 1.5 million cans every day. Here is how the can looks at different stages. From a sheet of metal to a can that's ready to hold your beans. Large metal sheets arrive at the factory from lots of different countries around the world, including China and Brazil. First, they are cut into small rectangles by this special machine. Each of these rectangles will become a can. Next, the smaller rectangles of metal are taken to this machine, where they are bent around a cylinder to make a tube shape. The edges are then soldered together by this machine. The metal can now hold its shape without falling apart. The can then passes into this machine, which strengthens it by adding these ribs called beads. Next, this machine makes the lids and bottoms by punching out the shape from sheets of metal, like this. Finally, once all the parts are made, the bottom is attached to the can using heat. The can is now ready to be filled with beans and the lid attached, ready to be delivered to stores for you to buy.
Right, that was a very nice, clear show of how cans are made. Now, let's just describe that again. So we take a coil of tin plate, we cut it into a size, and we accumulate that, and then we print on it. We size it, print on it, as I've explained. We then cut out each blank. If in this case is 1, 2, 3, 1, 2, 3. So there are 9 blanks in this sheet, which means we'll make 9 cans out of that sheet. We then take each blank and we roll it. We roll it and we weld it on the side. We then flange it, and then we take another strip of material from there and we punch out the ends. So these are the ends. The pieces that go on the top and the bottom are called the ends. These are then attached to the body by means of a double seam process. Now, this is a typical example out of a factory in South Africa where these cans are printed, and you can see on this piece of metal sheet here, we have 1, 2, 3 Velvet Glow cans. So these cans are 5-liter cans. So this is a 5-liter paint can. So we can only make 3 out of 1 sheet. Now, once these are cut in the middle, they cut apart, you will end up with a one Velvet Glow can blank like this. We call them a blank. In the industry, it's called a blank, B-L-A-N-K. This blank is then folded over or rolled over, and it is side welded here. You can see my cursor. It's side welded here along this line. Now, I am not able to give you a lot of detail about this because then I can keep you here for hours. In fact, I think I'm already going to overshoot. Alex, will you please just tell me to stop when you are ready for the next speaker? Because you know me, I can go on. This quality of the welding here is extremely technical. We have what is known as a butterfly weld, where the number of nuggets. So when you weld along the length here, you weld and you stop weld and you weld and stop weld. It's called a nugget weld. So we can count the number of nuggets in a meter length, in a meter per meter, or the number of nuggets per 10 centimeters or whatever. And there is a specification for that. The higher the number of nuggets, the better will be the weld, depending on the application. Now, there are things, welding, which is called a Wima weld, which is a highly sophisticated weld. And then where we are needing aerosols, we use what is known as a super Wima weld. Wima, W-I-M-A weld. Super Wima, S-U-P-E-R, W-I-M-A weld. So you can look at that at your leisure. Otherwise, I'd keep you here forever if I have to discuss the technicalities relating to welding in metal containers. What we then do is we have a can like this, which is now round and it's welded on the side. Oh, this is where we protect the weld, both on the inside of the can and on the outside. We protect it with a spray, which typically could be an epoxy phenolic spray. And this spray will then protect the weld from attack from water or humidity. So this is a can that that's how it looks. Now we flange. So we see the top. Let me show you the top here. You see the top is just ending up straight here. But if I bend this around, it'll have it look like this, won't it? This is known as a flange. Now the flange is also at the bottom and the top. Why do we flange? We flange so that we have material from the body that will now be part of the double seam, together with the material that is coming from the end. Sometimes we use the word component or end. So here's an end. This is the top end, and this is the bottom end. Both these ends need to be sealed onto this can. This one will go on the top. This is called a ring, by the way. It goes on the top here, and the ring is seamed on, and then the end is seamed on. Why it's called a ring? Because it looks like a ring. But once you seam it on, you can then put the lid onto the ring, and the ring is attached to the body. You get it? Don't tell me now why it's not called a 4-piece can, because you have a lid and a ring and a body and a base. You can't argue that with me. I won't have an answer for that. It's just called a 3-piece can. The top is known as 1 piece, although it's 2. Now, when you put the top and the bottom on before the double seaming, this is how it looks. Then this unit with the top and the bottom goes into a machine, and then it comes out flattened like this. You see? Watch. Here it is. You can see here, this is the flange underneath here, and there's the ring sitting on the top. There is a bit of overlap of these materials before double seaming. After double seaming, this is what happens. The ring. Sorry, did somebody ask some question?
Yes, there are some questions. Let me just take the questions.
Sure.
If you want to take them later. The first question has to do is from Bakri Wahid. He said, why do we have on the side and base wells despite protection with lacquer? Is there other better option? Then the second question is...
sorry, Alex, just what is the first question?
The first question is, why do we have rust?
Oh, rust.
As in corrosion on the base well despite the protection by lacquer?
Right. Let me just answer that question quickly. Okay, ultimately, we are working with steel, and steel is subjected to, when it is subjected to water, water vapor, humidity, relative humidity in the air, it will, there is no doubt about it, it will start oxidizing. Rust is another word for oxidizing. Oxidation is when the atmospheric oxygen eats into the tin plate. Now, this also can come from water, because water is made up of oxygen and two hydrogens, or H2O. So this will eat into the can. What we do is by spraying the can, firstly with the paint, 6 or 8 colors. Remember, we got a base coat, we got 6 or 8 colors. Then we spray an over varnish as well. These materials tend to protect the can. The ends of the can have only one layer or 2 layers. It'll have a white coating and a varnish on it. And it's very likely, depending on where you're storing the cans, the relative humidity, the temperature, it's possible that the can ends could rust. So this is why we protect it, but we cannot guarantee it. But we do guarantee at least 12 to 24 months shelf life. That's more the interior of the can not reacting with the paint and the paint not eating into the can. That's what we talk about there. But if you leave the paint out in the rain, within the 12-month shelf life, you could get rusting. Although now I must say that the cans are very, very well protected. So this is now the finished packaging that has the double seam on the top and the bottom. Here is the double seam at the bottom. Here, let's not worry about this. These are all welding opportunities, but we don't use this that much now. Here is the double seam, and in the double seam, here's the flange of the body. Here's the body with the flanged material. Here's the end that is sitting on top. In the double seaming process, there are 2 operations. In the first operation, the metal is introduced to each other, and in the second and the final operation, they're bound together tightly. What happened to this rubber compound that's lining here, a lining compound? You will notice in the first introduction, it starts to smear itself around the metal. When it is compressed, it forms an airtight seal. That is known as a hermetic seal that I was talking about. This is a cross-section of the double seam. Can you understand what happens in the double seam? Here's the body. There's the body that goes up and it forms a hook. We call this the body hook. Then there's the end which comes to the body. At a point, it picks up, it goes around the body hook, comes around, and it forms what is known as another hook. This hook is called the cover hook. So you have a body hook and a cover hook. And very important to the guys, the quality guys that look and test the double seam, is the overlap between the body hook and the cover hook. As shown in this sketch, here is from the other side, the component is coming through to the body. There's the body is going up. It's the other way around, it's laterally inverted. The body is going up and it forms a hook. So how many pieces of metal are there? How many sides of metal are there? There's 2. Here, in the end, you come up, you go around the body hook, and you form another hook. It's called the cover hook. So here you have the cover hook length. Here you have the body hook length. Take a minute or 2 and look at that graph or the sketch. The cover hook length starts from there to there, and the body hook length starts from there to there. And there to there is overlap. It's called a hook overlap. By the way, anybody wants to guess how many millimeters we are talking about? How many millimeters thick and how many millimeters long do you think this is? Any guesses? So generally the seam length will be about 2 to 3 millimeters. Depending on the size of the can, it could be 4 millimeters as well. And the thickness will be probably about 1 millimeter. How is the thickness calculated? The double seam thickness is equal to 3 times the end thickness. Here's the end of the component. That's 1, that's 2, and that's 3. So it's 3 times the end plus 2 times the body wall. There's the body, 1, and down the hook, 2. So 3 times the end plus 2 times the body wall. And of course, whatever little bit and pieces of the sealing compound is smashed inside there. Typical failures would be a weld leaker, rivet leaker, false double seams, a barcode failure. So when we print the can, the barcode may fail, and this is regarded as a failure of the entire can. A false double seam means that the double seam didn't work very well. You didn't get a clean double seam like this. This is a proper clean double seam. There are many things that could go wrong in this double seam. So that could be a false double seam, barcode failure, PC6000 Hexicon verification. If you guys don't know this, you might want to just write this down. If you want to verify a barcode, you'll use a PC6000 Hexicon verifier, a very, very powerful tool. This tells you what the whether the quiet zones are right, whether the bar width reduction is right, whether the density is right. There's a whole lot of things that the machine can teach you and tell you about. Then, of course, you could have color variation on the graphics. That's also a failure, where we use a digital color measurement, which is digital spectrophotometry, which I'm not going to go into detail now. And then you have the beverage can. So, sorry, that brings me to the end of tin plate or steel packaging. Let's talk aluminium now. We have beverage cans, monoblock aerosol cans, and then, of course, these things you don't really worry about. Automotive oil filters in your car engine. That oil filter is an aluminium packaging. And fire extinguishers that you see in your buildings, those are also made of aluminium. So let's quickly look at the aluminium. The aluminium aerosol can. The aluminium aerosol can is made from a disc like this. You may not believe me, but the aerosol cans, the typical aerosol cans that you would, and I'm sure Alex, there is Axe, Unilever's Axe cans in Nigeria.
Yes, we'll try and visit the Nampak factory here, and then maybe one of that factory so they can have the
very good.
Yeah.
Yeah, but this is what is known as an aluminium slug. Now it looks like a coin, like a money coin, but the typical can diameters is 35 millimeters, 45 millimeters, maybe 50 or 53 millimeters. And the thicknesses range from about 4.5, 5 millimeters, 5.8, 6.2, 7.5. You won't get, very unlikely to go and get an 8 or a 10 millimeter unless you are extruding a very long can. Now, what I need to tell you is that the can diameter is a function of the slug diameter. If you want a 53 diameter can, you will have to use a 53 diameter slug. If you want a 35 diameter can, you use the 35 diameter slug. Now, if you are making a 45 diameter can and you're using a 45 diameter slug, next question is, how tall is the can? Do you want 100 millimeter tall, 120, 150, 180? Now, the height of the can, of the extrusion, is then determined by the thickness. Because the material, ultimately, of the tube, the can, the one that you're going to spray the perfume, all that material is inside the slug. So let me tell you something else which will shock you. I can tell you, when I look at the can, when I analyze the can, I will tell you which part of the slug the material of the shoulder came from. Which part of the slug is the base of the can coming from? Which part of the slug is the top wall coming from? which part of the slug here is the bottom wall coming from? I can tell you exactly. We can profile this thing, which, okay, we don't want to talk too much detail now. I'll just leave you with this thought that aerosol manufacturing is a very complicated process. Now, when you take that, I'm going to show you a sketch, a film of this thing now, so you'll see it properly. Here is the slug. This is the same slug, this slug. When we put it into the press in a tooling, which is known as a male and female tooling, we put the slug in between the male and female tooling. Then we bring the male into the female, and the aluminium slug is in between there. It has no place to go except through the clearance. And that is known as the impact backward extrusion or backward impact extrusion. What is the force? 200 tons. Let me just say that again. Not 1 ton, 200 tons of ram hits the slug in the tooling. The slug is bamboozled. It doesn't know what to do. It immediately flows out like a liquid aluminium, and it forms this. First, it will look like this. Then we trim the top off, and it looks like this. Once we, of course, this thing, there's two things that happen here. We trimmed it, and we then cleaned it on the outside through a rotational wheel, and so it becomes nice and shiny. The next stage, we take the empty can, and we inside the can wear internal lacquer. The internal lacquer is an epoxy phenolic lacquer. We then print the outside of the can. We coat it first with a white coating. We then print 5, 6, 7, 8, sometimes even 9 colors onto the can. We then shape it on the top into, so it's called a neck profile, the necking profile. Various shapes. This is the axe can. You could have a can, which is a gorge profile, a totally different profile. You could have a round shoulder, bullet shoulder, a square shoulder, flat. I mean, you just walk into the aerosol pharmacy or whatever, wherever you can get these things, and look at the different profiles. So the next time you spray an aerosol, take care to consider the detail that has gone into it. Now, some of the advantages of aluminium packaging: very light, reduced transport costs, soft, ductile, shiny, attractive. And when alloyed, the strength of the aluminium is increased. Of course, when it's in its pure aluminium state, it is a bit weak because it's very soft. And aluminium does not rust. But tin plate will rust. So there's a question for the gentleman that asked me about rusting. And what is the disadvantage? Cannot be soldered or welded. That's why we make it from a monoblock. This is, by the way, this is known as a monoblock. Why is it known as a monoblock? Because it comes from one piece, the slug. Mono means one, monoblock. And the other disadvantage is aluminium, a little bit more expensive than tin plate. So what are the things that we check? Base thickness, wall thickness, the trim length, internal lacquer, decoration, and the factory finish can height. In other words, the height of the can. The curl diameters, contact height. The contact height is an imaginary point at the inside of the can where when the can is filled with the perfume and then the valve is crimped on. The valve crimp depth and diameter is crucial. Because if you don't clinch, it's called a clinching. If you don't clinch, watch my fingers. What has happened inside the can, there's a tool that opens the valve inside the can. It's called a clinching tool. When it opens the valve, it then gets, here's what happens. The valve sits inside here. And the tool goes in and it opens inside, which means that the valve is then clinched onto this point. You see this point here and this point. And therefore, the valve can never come out of the can because it's clinched from the inside. a very, very technical process, which we don't want to go into too much details. Currently, because of light weighting and because of really sustainable development goals and environmental sustainability issues, the entire world, the aerosol manufacturing world, has light weighted all the cans down to a point where it's really, really light. An aerosol can doesn't weigh much now. Typical brut can, 23 grams. X can, or 25 grams. Nothing. 25 grams. It's nothing. Not even 100 grams. Right.
The next time you buy a canned soft drink.
By the way, I'm just shifted away from aerosols. Oh, there's something which I didn't show you, which I have to show you. So you'll just forgive me if I just quickly find another. Yeah, I'm seeing, I just realized that one of my videos are not there. So I will try to.
Sorry, there is a question for you.
Yeah, you can shoot while I'm doing this. Fine.
Okay.
Yeah. What's the question?
Yes, sir. Events and things have shown that while for parents, while we drink at home, sometimes we buy canned drinks. So our children, they want to take these canned drinks. So what is the manufacturing industry doing to take safety into cognizance while children of about maybe 2 years old to 5 years old drink this can, and it will be safe for them? Because I have noticed sometimes that these cans they injure children. So for the safety of children, are they putting it into the manufacturing of cans? That is my question.
But what is the injury safety factor with the can at the moment? You're talking about the beverage can, drinking beverages. You mean by drinking through the?
Yes, not for adults, but for children, because when they put their mouths there, it has happened, which I am a witness. It cuts the tongue. I mean, they are not careful, and I don't know, but I think it's from the design. It's too sharp from where is going into the mouth. So yeah, look, that's a good question, but yeah, I must actually show you something. I'm not sure if I've got it here. Look, the short answer to your question is, I would strongly recommend that a 3-year-old is not given a beverage can to drink directly out of. You pour it out into a glass or into a baby cup and you let him or her drink from there. That can is intended for an adult drink. And it's going to be almost impossible to go, because remember, the point at which you drink out of, in the first place, even an adult should decant the product. You see, there is a video that I've got which shows you how the lever principle operates to open the can. The can is it is semi-cut, and that is done. That incision or cut on the metal of the end, the top end, is done to such precision. So if it is
If the end is 22 microns or 220 microns or 200 microns, you're going to get a cut which is about 11 or 12 microns, which leaves the other 11 microns intact, sealed. When you press the button to break the seal, you have to break the metal. Therefore, the metal will always be in its sharp state, and it could injure the child. So I would strongly recommend that it's poured out into a glass. This video is a video that shows you how the aerosol can is made. Is that better?
Yes, yeah, sure. We did the audio. We can't hear.
No, audio is coming. The audio is nothing there at the moment. Can you hear?
Okay, yeah, that's. we can hear you.
Okay. Okay. Any questions on that video?
Any question?
That is a video now that shows you exactly how an aerosol can is made. I showed you a pictorial, but that's the actual. Yeah.
Good afternoon, Mr. Singh.
Hi.
Hi. Just a quick question. What is the minimum thickness you can go with the aluminum can and a tin plate can?
Right. That's an excellent question. So typically, the way I'm going to have to answer the question is a bit like this, twofold. Number one, the aluminum can, I didn't specifically mention this because I didn't want to confuse the issue, but now that the question has come up, in an aluminum can, the base thickness exceeds the wall thickness, number one. So the base thickness is typically 0.75 to 0.8 of a millimeter, 700 microns. Then on the wall, at the bottom, you could go down to 0.21, 22. It's 220 microns. On the top, you may get 280 microns. Why, you may ask, is the top thicker? It's because of the shaping. There's quite a lot of effort and forces exerted on the top to obtain the necking profiles. That's why we need to keep the top walls a bit thicker. So why don't we keep the whole wall the same thickness? No, simply because we'll be wasting material. So we've got to, 2/3 up the wall, we've got to keep it as low as possible, around 0.25, 0.24, and then above that, 0.27, 0.28. That is about the thickness you will achieve. You probably can get down to 0.65 on the base and probably 2.021 on the bottom wall and 2.425 on the top wall. Very, very interesting video. Watch this.
The ingenious design of the aluminum beverage can. Every year, nearly 500 billion of these cans are manufactured. That's about 15,000 per second. So many that we overlook the can's superb engineering. Let's start with why the can is shaped like it is. Why a cylinder? An engineer might like to make a spherical can. It has the smallest surface area for a given volume, and so it uses the least amount of material. And it also has no corners, and so no weak points, because the pressure in the can uniformly stresses the walls. But a sphere is not practical to manufacture, and of course, it'll roll off the table. Also, when packed as closely as possible, only 74% of the total volume is taken up by the product. The other 26% is void space, which goes unused when transporting the cans or in a store display. An engineer could solve this problem by making a cuboid-shaped can. It sits on a table, but it's uncomfortable to hold and awkward to drink from. And while easier to manufacture than a sphere, these edges are weak points and require very thick walls. But the cuboid surpasses the sphere in packing efficiency. It has almost no wasted space, although at the sacrifice of using more surface area to contain the same volume as the sphere. So, to create a can, engineers use a cylinder, which has elements of both shapes. From the top, it's like a sphere, and from the side, it's like a cuboid. A cylinder has a maximum packing factor of about 91%, not as good as the cuboid, but better than the sphere. Most important of all, the cylinder can be rapidly manufactured. The can begins as this disc called a blank, punched from an aluminum sheet about 0.3 of a millimeter thick. The first step starts with a drawing die, on which sits the blank and then a blank holder that rests on top. We'll look at a slice of the die so we can see what's happening. A cylindrical punch presses down on the die, forming the blank into a cup. This process is called drawing. This cup is about 88 millimeters in diameter, larger than the final can, so it's redrawn. That process starts with this wide cup and uses another cylindrical punch and a redrawing die. The punch presses the cup through the redrawing die and transforms it into a cup with a narrower diameter, which is a bit taller. This redrawn cup is now the final diameter of the can, 65 millimeters, but it's not yet tall enough. A punch pushes this redrawn cup through an ironing ring. The cup stays the same diameter as it becomes taller and the walls thinner. If we watch this process again up close, you see the initial thick wall and then the thinner wall after it's ironed. Ironing occurs in 3 stages, each progressively making the walls thinner and the can taller. After the cup is ironed, the dome on the bottom is formed. This requires a convex doming tool and a punch with a matching concave indentation. As the punch presses the cup downward into the doming tool, the cup bottom then deforms into a dome. That dome reduces the amount of metal needed to manufacture the can. The dome bottom uses less material than if the bottom were flat. A dome is an arch revolved around its center. The curvature of the arch distributes some of the vertical load into horizontal forces, allowing a dome to withstand greater pressure than a flat beam. On the dome, you might notice two large numbers. These debossed numbers are engraved on the doming tool. The first number signifies the production line in the factory, and the second number signifies the body maker number. The body maker is the machine that performs the redrawing, ironing, and doming processes. These numbers help troubleshoot production problems in the factory. In that factory, the manufacturing of a can takes place at a tremendous rate. These last three steps, redrawing, ironing, and doming, all happen in one continuous stroke and in only a seventh of a second. The punch moves at a maximum velocity of 11 meters per second and experiences a maximum acceleration of 45 Gs. This process runs continuously for 6 months, or around 100 million cycles before the machine needs servicing. Now, if you look closely at the top of the can body, you see that the edges are wavy and uneven. These irregularities occur during the forming. To get a nice, even edge, about 6 millimeters is trimmed off of the top. With an even top, the can can now be sealed. But before that sealing occurs, a colorful design is printed on the outside. The term of art in the industry is decoration. The inside also gets a treatment. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a metallic taste and also keeps acids in the beverage from dissolving the aluminum. The next step forms the can's neck, the part of the can body that tapers inward. This necking requires 11 stages. The forming starts with a straight-walled can. The top is brought slightly inward, and then this is repeated further up the can wall until the final diameter is reached. The change in neck size at each stage is so subtle that you can barely tell a difference between one stage and the next. Each one of these stages works by inserting an inner die into the can body, then pushing an outer die, called the necking sleeve, around the outside. The necking sleeve retracts, the inner die retracts, and the can moves to the next stage. The necking is drawn out over many different stages to prevent wrinkling or pleating of the thin aluminum. Since the 1960s, the diameter of the can end has become smaller by 6 millimeters, from 60 millimeters to 54 millimeters today. This seems a tiny amount, but the aluminum can industry produces over 100 billion cans a year, so that 6 millimeter reduction saves at least 90 million kilograms of aluminum annually. That amount would form a solid cube of aluminum 32 meters on a side. Compare that to a 787 Dreamliner with a 60-meter wingspan. Now, after the neck has been formed, the top is flanged. That is, it flares out slightly and allows the end to be secured to the body, which brings us to the next brilliant design feature, the double seam. On older steel cans, manufacturers welded or soldered on the ends. This often contaminated the can's contents. In contrast, today's cans use a hygienic double seam, which can also be made faster. This can is cut in half so you can see the cross-section of the double seam. To create this seam, a machine uses two basic operations. The first curls the end of the can cover around the flange of the can body. The second operation presses the folds of the metal together to form an airtight seal. While the operations themselves are simple, they require high precision. Parts misaligned by a small fraction of a millimeter cause the seam to fail. In addition to the clamping of the end and can body, a sealing compound ensures that no gas escapes through the double seam. The compound is applied as a liquid and hardens to form a gasket. The end, attached immediately after the can is filled, traps gases inside the can to create pressures of about 30 psi or 2 times atmospheric pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, nitrogen is added. So why is a beverage can pressurized? Because the internal pressure creates a strong can despite its thin walls. Squeeze a closed pressurized can, it barely gives. Then squeeze an empty can. It flexes easily. The can walls are thin, only 75 microns thick, and they're flimsy. But the internal pressure of a sealed can pushes outwards equally and so keeps the wall in tension. This tension is key. the thin wall acts like a chain. In compression, it has no strength, but in tension, it's very strong. The internal pressure strengthens the cans so that they can be safely stacked. A pressurized can easily supports the weight of an average human adult. It also adds enough strength so that the can doesn't need the corrugations like in this unpressurized steel food can. While initially pressurized to about 2 atmospheres, a can may experience up to 4 atmospheres of internal pressure in its lifetime due to elevated temperatures, and so the can is designed to withstand up to 6 atmospheres or 90 psi before the dome or the end will buckle. Why is there a tab on the end of the can? It seems a silly question. How else would you open it? But originally cans didn't have tabs. Very early steel cans were called flat tops for pretty obvious reasons. You use a special opener to puncture a hole to drink from and a hole to vent. In the 1960s, the pull tab was invented so that no opener was needed. The tab worked like this. You lift up this ring to vent the can and pull the tab to create the opening. Easy enough, but now you've got this loose tab. The cans ask you to please don't litter, but sadly these pull tabs got tossed on the ground where the sharp edges of the tabs cut the bare feet of beachgoers or they harmed wildlife. So the beverage can industry responded by inventing the modern stay-on tab. This little tab involved clever engineering. The tab starts as a second-class lever. This is like a wheelbarrow because the tip of the tab is the fulcrum and the rivet the load. The effort is being applied on the end. But here's the genius part. The moment the can vents, the tab switches to a first-class lever, which is like a seesaw, where the load is now at the tip and the fulcrum is the rivet. You can see clearly how the tab, when working as a wheelbarrow, lifts the rivet. In fact, part of the reason this clever design works is because the pressure inside the can helps to force the rivet up, which in turn depresses the outer edge of the top until it vents the can, and then the tab changes to a seesaw lever. Looking from the inside of the can, you can see how the tab first opens near the rivet. If you try to simply force the scored metal section into the can using the tab as a first-class lever with the rivet as the fulcrum throughout, you'd be fighting the pressure inside the can. The tab would be enormous and expensive. If you'd like to learn more about the entire life cycle of the aluminum can, watch this animated video by Rexam that describes can manufacturing and recycling. A typical aluminum can today contains about 70% recycled material. Also, Discovery's How It's Made has some great footage of the manufacturing machinery. Here are 2 different stepwise animations of the entire can forming process. And lastly, these are 2 detailed animations of the cup drawing and redrawing processes. The aluminum beverage can is so ubiquitous that it's easy to take for granted. But the next time you take a sip from one, consider the decades of
We put our hands together for Kishan.